Hi, in this video, we are going to talk about the relation between the sign of f prime and the functions being increasing or decreasing. Also, there is a relation between the sign of f double prime and the concavity of the function f. Also, we will talk about first and second derivative tests for local maximum and minimum. And finally, we are going to have an example for sketching graphs of functions. So first of all, we have some bunch of definitions. One of them is a function f is called increasing on an interval a to b if f of x1 is less than f of x2 for all x1 less than x2 in the interval. So if x1 increases to x2, then f of x1 increases to f of x2. So we have three types of increasing functions. If we just look at them locally, one of them is like the first picture, one of them is like the middle, and the third one is like the rightmost one. So all of these functions are increasing because when you increase from x1 to x2, f of x1 increases from f of x1 to f of x2. So, but the difference between these three functions are actually determined by the concavity, which will be related with their second derivatives, but we'll come to that. And then a function is called decreasing on an interval if f of x1 is bigger than f of x2 when x1 is less than x2 in the interval. So now in this case, we are going to have decreasing graphs, like, you increase from x1 to x2, but then f of x1 is bigger than f of x2. Actually, f of x2 gets smaller than f of x1. So there are three possible ways again. So all of these three pictures are decreasing function pictures, but the difference between them is their second derivative again. But again, that's going to be talked just later soon. So then there is a relation between the sign of f prime and whether a function is increasing or decreasing. So that's a theorem, but let f be a differentiable function on an interval a to b, then f can be, if f is increasing on an interval, then f prime is positive on that interval. So look at these three increasing function pictures we had, and then draw tangent lines at any point. Like we have an increasing function. If we draw the tangent lines at x1 and x2, as you see, all of the tangent lines are going upwards. So a tangent line going upwards have positive slope. So positive tangent line slope means derivative positive. So if f is increasing, the tangent lines will be positive slope, or they will be going upwards, so positive slope, so derivative will be positive. Or you can go vice versa, that's also true. If the graph of the function f always have positive tangent line slopes, then the function must be increasing, okay? And if f is decreasing on an interval, then derivative must be negative. Why? Think about our decreasing function pictures. Draw the tangent lines. Well, the tangent lines will be going downwards. That means they have negative slopes. So negative tangent line slope means derivative negative. So that's why we have sign of derivative negative. But you can also go backwards. If f prime is negative, then that means all of the tangent lines to the graph of f are going downwards. That means the function must be decreasing. Okay. So now here is an example. Find the intervals where f is x squared is increasing and decreasing. So let's say f prime, well, since increasingness and decreasingness is related to the sign of f prime, we find f prime, which is 2x. So this 2x, if this is positive, then f will be increasing. So when is 2x positive? 2x is bigger than 0. Well, that's only possible when x is positive, when x is bigger than 0. So for all numbers on the interval 0 to infinity, f prime will be positive, which means f is increasing. So for all numbers, if f prime is negative, then the function will be decreasing. So 2x, when can it be negative? For all the numbers when x is less than 0. So for negative numbers, 2x will be also negative. So f prime will be negative. That means f is decreasing. So we say that f is decreasing on the interval minus infinity to 0. Okay, another definition is the concavity. So what is concavity? We can have two possible actually three types of concavities, but two are more common. So f is called concave up on an interval if the graph of f stays above the tangent lines to the graph. Okay, so if the graph of f stays above all the tangent lines, then f is called concave up on that interval. If f is called concave down on the interval if the graph of f stays below the tangent lines to the graph on a to b. So look at concave up. Like if you have a concave up graph, then the graph stays above the tangent lines. Look at this picture here. If you have a concave down picture, then the graph stays below the tangent lines. Now, the theorem says there is a relation between the concavity of f and the sine of f double prime. So this theorem is that theorem. And so we say that f is concave up on interval a to b if and only if f double prime is positive on the interval. So how does this happen? Now let's look at this picture here. Now let's have a concave up graph like the red picture here on the top. And then draw tangent lines from x1, x2, x like at the points x1, x2, x3, x4, x5, which are in the interval. When you draw the picture here, like at x3, the tangent line is horizontal, so derivative is 0. But at x2 and x1, the tangent lines are going down, so they must have negative slopes. But compare x1 and x2, the slopes of tangent lines at x1 and x2. x1 is more negative, x2 is less negative. So you can say, you can make an ordering. F prime x1 is the most negative, and then comes f prime x2, but f prime x3 is 0, which is bigger than the first two. And then look at the tangent line slopes at x4 and x5. Like at x4, the tangent line is positive, but at x5, tangent line must be more positive, bigger than the tangent line slope at x4. So we can compare the slopes of tangent lines at x4 and x5, which are f prime x4, x5, f prime x5. So what is happening here? When we increase the x values, x1 increases to x2, then to x3, then to x4, then to x5. Well, f prime values also increase. So if a function is increasing, then what do we say? Its derivative is positive. Well, if f prime is increasing, then its derivative, which is second derivative, must be positive. Here, look at the graph of the derivative here. We have something negative at x1, something less negative at x2, 0 at x3, f prime, something positive at x4, something more positive at x5. So if we sketch a graph of f prime, we are going to see a graph like this, which is increasing. F prime is increasing. So its derivative must be positive, but derivative of first derivative is second derivative, positive. So if f is concave up, second derivative is positive. Now, in a similar way, we can also see if f is concave down on an interval, then f double prime is negative on that interval. Now, how? Let's have a concave down graph like this, and then draw the tangent lines at x1, x2, x3, x4, x5. As you see, x1, x2, x3, x4, x5, this is in the increasing order. So we are increasing x values. But what happens to the slopes here? The slope at x1, the slope of the tangent line at x1 is something positive. At x2, also positive, but must be smaller slope than the slope at x1. At x3, the slope must be 0 because it's a horizontal tangent line. At x4, it must be a negative slope tangent line. At x5, also negative, but more negative than the previous one. So if we look at the graph of f prime, it starts from positive at x1 and then it gets less positive, 0 at x3, well, negative at x4, negative, more negative at x5. So it's going to give us a graph like this, which is a decreasing graph for f prime. So if f prime graph is decreasing, then what can we say? If a function is decreasing, then its derivative is negative. But if f prime is decreasing, then its derivative, which is second derivative, must be negative. So if f is concave down, f prime will be decreasing, so f double prime will be negative. Okay, another definition is, actually this is the last definition. This is a definition of inflection point. So a point x equals d is called an inflection point of f if the concavity of f changes after x equals d. So if the concavity changes at a point, then that concavity change point has a special name, inflection point. We don't say concavity change point, we just say inflection point. Look at this point D here. Before D, it's concave down. After D, it's concave up. And look at the tangent line picture there. Like one side of the tangent line stays above the graph, so that's concave down part. And look at the right side. The tangent line stays below the graph. That's the concave up part. Okay. Now, another example. Find the intervals where f is concave up or down, and the inflection points of f if the function is x cubed. Okay, now first, to talk about concavity and the inflection points, we need to look at the second derivative. So we find the first derivative, that's 3x squared. Then we find the second derivative, that's 6x. Now, if second derivative is positive, the function will be concave up. So when can be 6x positive? If x is positive, 6x will be also positive. So if x is positive, f double prime will be positive. So on the interval from 0 to infinity, f is concave up. And then if we look at second derivative, and if second derivative is negative, then f will be concave down. So when can 6x be negative? If x is negative, 6x will also be negative. So if x is less than 0, then f double prime will be negative, which means on the interval minus infinity to 0, because x less than 0 means negative numbers, x greater than 0 means positive numbers. So for positive numbers, f double prime positive, so f concave up. For negative numbers, f double prime negative, so f concave down. And then where did the concavity change? At 0, right? At 0, concave down changed to concave up. Look at the graph actually. We know the graph of x cubed. It looks like a picture like this. As you see, before 0 or negative numbers, it's concave down. And look at it, it's concave down, so second derivative will be negative. At 0, there is a concavity change. After 0, it's concave up because second derivative will give positive sign. And look at the tangent line there at 0. On the left, it is above the graph. On the right, it's below the graph. That's exactly what happens at an inflection point. Okay? And then these two tests, which are actually important. These are first derivative tests and second derivative test. But first derivative test is if we have a critical point of f, then that critical point is a local maximum if f prime changes sign from positive to negative. Okay, so look at these two pictures. We have two possible pictures because we can have two kinds of critical points. In the first case, f prime at c is 0. That's a critical point, horizontal tangent line. In the second case, f prime doesn't exist. It's a broken graph. But doesn't matter. Look at the graph. Look at the graphs. In both pictures, before c, f prime must be positive. Why? Because f is increasing. If f is in both pictures, look at the picture, f is increasing, so f prime must be positive before. And in both pictures, if you look at the graph, the function is decreasing. So f prime must be negative. Decreasing function gives negative derivative. So f prime positive changes to negative. And in both pictures, as you see, it gives a local maximum. So x equals c is a local maximum point. And if you find f of c, then you are going to find the local maximum value. Well, the second part is for the local minimums. So if f prime changes sign from negative to positive, then it's a local minimum. So look at both of the pictures again. in the first case, f prime is 0, horizontal tangent line. It's a critical point at C. And look at the second one. F prime C doesn't exist because broken graph. But in both cases, the function is decreasing before the critical point and then it's increasing after the critical point. So f prime changes from negative to positive, right? So this is called first derivative test. Here is an example. Use the first derivative test to find the local maximum and minimum points of the function x cubed minus 3x. Okay, first we need to find the critical points. So, well, it's a polynomial, so we can only have f prime equals 0 kind of critical points because f prime will always be another polynomial, and polynomials, they exist at every point. So f prime c can be 0 for a critical point, and that gives the equation 3x squared minus 3 equals 0. And then we factor that, it gives 3 times x minus 1 times x plus 1, and it gives x equals 1 or x equals minus 1. These are critical points. Now, if you want to use the first derivative test, we take 2 points, one before, one after each of the critical points. So for minus 1 critical point, if we take, let's say, minus 2, and then if we take 0, and if you look at the sign, if the sign, so we look at how the sign of f prime changes. Like, okay, we take minus 2 and 0. If you put them into the first derivative, f prime minus 2 is plus 9, so positive. F prime 0 is minus 3, negative. So positive changes to negative. Positive means before it is increasing, after it's decreasing. So it's a local maximum by the first derivative test. So at x equals minus 1, f prime positive changes to negative. So it's a local maximum at minus 1. What about for the critical point plus 1? Take 1 point before, which is 0. We already have the computation for 0. And then take a point after 1, let's say 2. You can take other points too. I mean, you can take other points you want, but I just take these points because they are easier to compute. But you can take other points in those intervals and you are going to get the same result anyway. So at x equals 1, we know that f prime of 0 is negative. But f prime of 2, if you compute f prime of 2, it's going to give plus 9, which is positive again. So before plus 1, negative, f prime negative changes to f prime positive. F prime negative means decreasing, changes to increasing. Think about it. It's a local minimum picture. So at x equals 1, we have a local minimum point. And if you sketch the graph of the function, you will see this red graph. And as you see at minus 1, there's a local maximum. Before the local maximum, increasing, after the maximum, decreasing. F prime positive changes to f prime negative. Look at the local minimum. Before the local minimum, decreasing, after increasing. So f prime negative changes to positive. So that's how we use the first derivative test. Now, there is also the second derivative test, which can be sometimes also very practical and useful. So this test says, if we have a critical point with f prime equals f prime at c equals 0, then there are two possibilities. If f double prime is less than, I mean, there are actually more possibilities, but if f double prime is negative, then it's a local max. If f double prime is positive, then it's a local min. Why? If second derivative is negative, what do we say? F must be concave down. And f prime is also 0. So f prime 0, f prime c equals 0 means the tangent line is horizontal. But then f double prime is negative. So it's a concave down graph. But where does this happen? At a local maximum point, this happens. Okay. And then for local minimum, if f double prime at c is positive, that means it's concave up. And f prime is 0 anyway, so tangent line is horizontal. Well, this happens at a local minimum. So if you look at the sign of the second derivative at the point f prime c equals 0, if you look at the sign of f double prime, positive gives local min. I mean, positive f double prime means concave up, that's a local minimum. Negative second derivative means concave down, that's a local maximum. So an example. Use the second derivative test to find out the local maximum and minimum points of f, x cubed minus 3x. So the previous example again. So we know that minus x equals minus 1 and x equals plus 1 are critical points of the function, because f prime at minus 1 is 0 and f prime at plus 1 is also 0. So now first derivative of this function is 3x squared minus 3 and the second derivative is 6x. So now plug minus 1 into the second derivative. That's going to give 6 times minus 1. That's minus 6, which is negative. So second derivative negative means concave down. Well, that's a local max. So x equals minus 1 is a local max point of f. Then plug the second critical point plus 1 into second derivative. That's 6 times plus 1 plus 6, positive. That's concave up, which means local minimum. So x equals 1 is local minimum. Again, remember the picture of that function. At minus 1, we had a local max, but that's a concave down graph there. So second derivative at minus 1 is also negative, as we found. And at plus 1, second derivative turned out to be positive, which is because f is concave up around plus 1. Okay. Now, the last part of this video is sketching graphs of functions. Well, what do? We do these 8 things. One of them is we find the domain of the function. We find the vertical asymptotes of the function, which, vertical asymptote means limit of the function when x goes to a, absolute value of f goes to infinity. So then we call x equals a as a vertical asymptote. The third thing we do is we look at the limit of f as x goes to minus infinity and plus infinity. So that gives us the end behavior. Minus infinity limit gives us the left end behavior. Plus infinity limit gives us the right end behavior of the graph of the function. The fourth thing we do is we find f prime and the critical points of f. So this can be f prime of c equals 0 or f prime c doesn't exist kind of points. And then we find the intervals where f is increasing and decreasing by just looking at f prime sign. F prime positive intervals will be f increasing intervals. F prime negative intervals will be f decreasing intervals. And then next we do find the local maximum and minimum points and values of the function using the first derivative test, because we will already have f prime information, so we can do that quickly. And then 7, we find the second derivative and the intervals where f is concave up and concave down, but how? We just look at the sign of second derivative. Second derivative positive will give us concave up graph parts. Second derivative negative will give us concave down parts of the graph. And then finally, since we already have made computations for the second derivative and found concave up, concave down intervals, that will also tell us quickly the inflection points where the concavity changes. We can also find the points, we can also find the values, inflection values. Then, if we gather up all this information, we can sketch the graph. For instance, let's take this function, x cubed minus 6x squared minus 15x. Sketch the graph. So the domain of this function, this is a polynomial. So polynomials are defined everywhere. So then the domain is all the real numbers or the interval from minus infinity to plus infinity. Well, is there any vertical asymptote? No. Why? Because polynomials, they are defined everywhere. They never get infinity for any finite number. So there is no vertical asymptote. What about the end behaviors? If we take the limit as x goes to minus infinity, this polynomial will go to minus infinity. Why? Because remember, the highest degree term determines what happens at the infinity. So x cubed is the highest degree term here. It's going to grow faster than the other two terms. So what happens to x cubed when x gets negatively very large? Well, it's going to be cubed. So minus infinity will be also minus infinity, because it's going to be like minus, if you multiply 3 times, you are going to get still minus. Something large cube will be something very large again. But when you look at x goes to plus infinity limit, x cube goes to plus infinity also. So the limit of the function is plus infinity, and x goes to infinity. So these are the end behaviors of the graph. And then we find the derivative of the function, which is 3x squared minus 12x minus 15. And then the critical points will come from f prime equals 0 only, because f prime is also a polynomial. There will be no such points where f prime doesn't exist. So only f prime c equals 0 can happen for critical points when f is a polynomial. So if we solve this equation, we get 3 times x plus 1 times x minus 5. So that gives two critical points, minus 1 and plus 5. And then to find out the intervals of f increasing or decreasing, we make a table. So there are 3 rows. First row is the interval of x, the domain, which is the domain of x, which is from minus infinity to plus infinity. That's always the first row in these tables. The second row is for the sign of f prime. But there are two critical points, minus 1 and 5. These critical points divide the interval into, divide the domain into 3 intervals, minus infinity to minus 1, minus 1 to 5, 5 to plus infinity. So there are 3 intervals. So for each interval, you can pick any random number you like. I picked here minus 2, 0, and 6, but you could have taken minus 3, let's say, plus 1, plus 2, or also you can take 7, 10. Doesn't matter. You would find the same signs. It doesn't matter. So pick the numbers which are, probably nicer than the others. So I just picked minus 2 and 0 and 6 from each interval. What do I do with them? I put them into the f prime. So I put minus 2 into f prime, 0 into f prime, 6 into f prime. Then I check for the sign. The minus 2, f prime at minus 2 is plus some number. So I put plus for that interval I picked minus 2 from. And then f prime 0 gives me minus 15. So that on that interval, f prime is negative. And then f prime 6 gave me something positive. Then on that interval, f prime has positive sign. Then if f prime is positive, f will be increasing, f prime negative, f will be decreasing. So the third row is for the intervals where f is increasing or decreasing. So we see that f is increasing on the first and on the third intervals, and f is decreasing on the second interval. So we can write this down. F is increasing on minus infinity to minus 1, and also 5 to plus infinity, because f prime is positive, and f decreasing on only minus 1 to 5 interval because f prime is negative there. So again, as I said, choosing different numbers from each interval will just give the same sign. It doesn't matter. And then the next thing, we want to find out local max and min. So we had two critical points, minus 1 plus 5. Actually, it's already visible from this third row here, like the function changes, the function changes from increasing to decreasing. That's gonna be a local maximum point. Also, look at 5. Function changes from decreasing to increasing. That's gonna be a local minimum. But from the first derivative test, f prime changes from positive to negative at minus 1. So it's a local maximum, we say, by the first derivative test. At 5, the f prime changes from minus to positive. We just say that's a local minimum. So that's the first derivative test. And if we have the local maximum at minus 1, we also need the local maximum value because we are going to sketch the graph. So f of minus 1 is equal to plus 8. We just said that x equals 5 is a local minimum. We plug it into 5. It's going to give minus 100. That's the local minimum value. So points are for the x coordinates, values are for the y coordinates. Now, next thing, we look at the second derivative of the function to figure out the concavity. So we differentiate the first derivative, we get 6x minus 12. So then we look for the zeros of second derivative. Well, 6 times x minus 2 equals 0, x equals 2. So there is a possible number 2. And again, we make a table for the sign of f double prime so that we are going to talk about in terms of concavity. Now, the first row is again the domain of f, which is from minus infinity to infinity. We got this number 2, which makes f double prime 0. And then f double prime is 0 at 2. But we want to find out the sign of f double prime on these two intervals. So I, again, pick any random number. And I choose possibly the nicest numbers I can, 0 and 3. Then I put these numbers into second derivative. And I got from 0, I will have 0, 6 times 0 minus 2, which is minus 12, negative number. So on that interval, f double prime is negative. For 3, I find 6 times 3 minus 2 plus 6 positive. So on that whole interval, second derivative is positive. Second derivative negative means concave down. Second derivative positive means concave up. There is a concavity change at 2, so x equals 2 is an inflection point. Anyway, so we say that f is concave down from minus infinity to 2, concave up from 2 to infinity. That's what we write here. And again, taking different numbers than 0 and 0 or 3 doesn't make any change. It's just going to give the same sign of f double prime. And we just said that, since there's a concavity change at x equals 2, it's an inflection point. Also, we plug this 2 into the function to get the inflection value. That's equal to minus 46. Now, if we use this information and sketch the graph of the function, what do we have? Well, before minus 1 to minus infinity, it's actually it's actually increasing from minus infinity to the local maximum, right? And then between minus 1 and 5, it's decreasing from minus 1 to 5. I should have a minus 5 here. And then it's increasing from plus 5 to plus infinity to plus infinity. So I will have a local max at minus 1, a local minimum at 5, an inflection at 2. So I'm going to have a graph like this.